Hello everyone, welcome back to the course on Introduction to Multi-Agent Systems. I am your course instructor Dr. Twinkle Tripathi. In today's lecture, we will continue discussing some more mathematical preliminaries, especially pertaining to the spectral properties of matrices. So before we do that, let us see why do we even need to analyze the spectral properties of a matrix. So let's look at this image. Now this image is from the movie 12 Angry Men, if you've seen it. So this image shows that there are a group of 12 people, supposedly angry people, who are having a discussion with each other and trying to see whether a consensus can be achieved on a certain matter. Now what we do is we try to represent these discussions or the group by a graph. So just as a representation, we have just shown a simple graph here, and we know that the nodes here represent the agents, or in this case of where we are looking at discussions among people. So we say the nodes represent the people and the edges represent whether they are talking to each other or not. Okay. Now, how do we go about modeling these discussions? One of the most popular models, or one of the earliest models that was proposed for this is the de Groot's model. So de Groot's model is a very simplistic model, but having said that, I'll quote George Box, who's a statistician, who once said that while all models are wrong, some of them are actually quite useful. So de Groot's model is one such model. So let us see what it looks like. So since we have already discussed this, it will be a quick recap. Now let's start by defining a social group which consists of n interacting individuals who are actually trying to update their opinions. The opinion vector x is actually an n cross 1 column vector. Every ith agent updates his or her opinion through an averaging process like this. Now every j here can belong to 1 to n. To be more precise, we can write j simply represents the people that I knows or is talking to. Is talking to. Now, using this simple averaging rule, we can arrive at nice conditions on when we can say that consensus is going to be achieved for this overall network. But before we can actually make these remarks, what are those conditions exactly which can guarantee when consensus can be achieved for this network? Let's try to simplify this a bit more. So here every xi is simply the ith person's opinion, but I can represent this as a vector in this form, which is our x. At every k plus 1th instant, is simply given by, just making this a bit more concise, it's given by this. What is A here? A consists of these entries aij, which simply represents how much a person, the ith person, trusts the jth person. That is what aij signifies. Now we see that ultimately the dynamics gets represented in the form of a matrix, or is governed by the matrix A. So what is the role that the matrix A exactly plays in ensuring consensus, or in arriving at rules which say that under these conditions consensus is guaranteed? So we'll try to analyze those things a bit more by zooming into such models. Let us see. So again, let us consider any discrete time linear system represented using this model. We know that one such example of it is the de Groot's model. what does the solution of this look like? Let's see. So, using this rule, x of 1 is simply x of 0, x of 2 becomes equal to, we can substitute this value of x1 here, which will give us, which is simply equal to, now we can keep repeating this process and this gives us the following result. At any given instant of time, x of k is simply given by a raised to the power k times x of 0. So, naturally this is a neat looking solution, but we still do not know a few things. For example, what exactly is the value of x of k to which this solution converges to as k tends to infinity? In other words, what is the steady state behavior of this system? Now, the answer to that is this. When I take limit k tends to infinity on both sides of this equation, so I know that since x of 0, which is the initial condition, is independent of time, the limit applies only to a to the power k, meaning the emergent or the eventual properties of a is what determines the behavior of x of k. So, when can I say the solution will converge? Definitely, it is something to do with the powers of a to the power k. So, based on this, now we introduce two definitions. The first is that of a semi-convergent matrix. The matrix A is said to be semi-convergent if, as k tends to infinity, the limiting value of a to the power k exists. It does not diverge, it exists. It is some finite value. Additionally, the matrix becomes convergent if not only does this limit exist, it is also equal to 0. So, how do we know when the matrix A is convergent and when it is semi-convergent, or when is it neither? Meaning, when will the solution converge and when will it diverge? So, how do we answer these questions? Now, in order to answer this, we will need to use a tool that is known as the spectral decomposition. So, what does the spectral decomposition look like? Let us see. To begin with, let us consider a square matrix A of size n cross n, which is symmetric, and let lambda I be its eigenvalues. So, how do we calculate the eigenvalues? I am sure most of you are familiar with this. We simply take the characteristic polynomial, which is given by determinant of lambda I, a minus lambda I. This is known as the characteristic polynomial. The variable here is lambda. Now, obviously, so the characteristic polynomial is of degree n, meaning we get n number of roots here, lambda 1 to lambda n, which are the required eigenvalues. And associated with each eigenvalue lambda, we have an eigenvector vi, which is simply calculated by setting avi equals lambda I vi. Using this, we can calculate the eigenvector associated with every eigenvalue lambda I. So, what is the spectral decomposition theorem? It goes this way. Now, for a given matrix A, which is symmetric in nature, there always exists a diagonal matrix J such that this relation holds. A can always be decomposed in this manner, which is a product of S, J, S inverse, where the J is always diagonal. And what is S? S is simply the matrix whose columns are the eigenvectors of the matrix A, meaning S can be written in this manner. where every Vi is nothing but the ith eigenvector. So, spectral decomposition theorem allows us to write A in a new form. Now, let us study some of the properties associated with this matrix J. Now, the matrix J is actually known as the Jordan matrix. So, they are also referred to as the Jordan normal forms. So, let us analyze a little more properties of the Jordan matrix J. Now, here notice that we have relaxed the condition of the matrix having to be a symmetric one. So, let us just start by any matrix A and let its eigenvalue as before be lambda I with corresponding associated eigenvectors being Vi. Then through simple rearrangement, just to recall, we had this relation through simple rearrangement, it can be rewritten in this manner. So, if we pre-multiply by this, we get, and similarly post multiplying S gives us the desired relation as given here. So, now if the matrix is not symmetric, is the matrix J always diagonal in nature? How can we determine these things? Now, the answer to this question actually lies in the eigenvalues associated with the matrix, meaning J, the structure of J actually depends on the nature of its eigenvalues, hence its eigenvectors too. So, let us see how that goes. But before we actually get into discussing what is the structure of J, let us introduce a few definitions pertaining to the eigenvalues of a matrix. So, it goes this way. Now, associated with every eigenvalue is its multiplicity. So, what are the kinds of multiplicities that we can associate with an eigenvalue lambda I? The first is known as the algebraic multiplicity, which is a very simple and standard definition. It is simply the number of times the root lambda is repeated, meaning if we have n number of roots. Now, suppose a few of them are actually the same, meaning let us say lambda 1 gets repeated 3 times. In this case, the algebraic multiplicity of lambda 1 is simply equal to 3. What is the geometric multiplicity? Now, the geometric multiplicity, it's a little bit more intricate. The geometric multiplicity is simply the number of linearly independent eigenvectors associated with the eigenvalue lambda. So, let us see a few examples of this. Suppose we have a matrix now its characteristic polynomial is equal to its determinant, and its roots can be found by setting it after setting it to 0. So, it simply becomes this, meaning the eigenvalues are 1 and 3. And so, how many times is 1 repeated? It is simply equal to 1. Similarly, the eigenvalue 3 is repeated once. So, Am of 1 is equal to 1. Similarly, Am of 3 is also equal to 1. Now, let us see one more example. Suppose now I change it slightly and make it equal to 1. So, now in the similar manner, the characteristic polynomial now becomes setting it to 0, we get that lambda equals 1 is actually repeated twice. So, what is its geometric multiplicity? Let us see. Now, in order to calculate that, we will have to first calculate the eigenvector associated with it. So, let us do that. Suppose I denote the eigenvector as some v and its two components given by v1 and v2, and it's equal to Av equals lambda v . So, simplifying it, we simply get these two equations, which actually, so if we choose the solution, we know it works. And if we choose another eigenvector as this, it also works. So, if you observe here, the eigenspace, which is simply the space containing all the feasible eigenvectors associated with an eigenvalue. So, if you see here, the eigenspace associated with eigenvalue 1 is actually equal to R2, meaning its dimension is 2. So, we can always associate two linearly independent eigenvectors with the eigenvalue 1, which implies that the geometric multiplicity of 1 here becomes equal to 2. So, depending on the algebraic and geometric multiplicities of an eigenvalue, we can further classify the eigenvalues a bit more. Let us see how we can do that. An eigenvalue is known to be, or is referred to as simple eigenvalue simply when its algebraic and geometric multiplicity is equal to 1. An example being this. Here it is repeated only once. So, then it is known as a simple eigenvalue. So, since it is repeated once, so trivially the geometric multiplicity is also equal to 1 for both 1 and 3. An eigenvalue is said to be semi-simple when its algebraic multiplicity is same as its geometric multiplicity, and both of them are greater than 1. Let us see an example again, which we just saw is this. So, here we know that the eigenvalue 1 is repeated twice. So, its algebraic multiplicity is 2, and through the calculations which we saw in the previous slide, we know that its geometric multiplicity is also equal to 2. So, such eigenvalues where the algebraic multiplicity is same as the geometric multiplicity, but both of them are greater than 1, then the eigenvalue is referred to as a semi-simple eigenvalue. Then the spectrum is simply the set of all of the eigenvalues associated with a matrix A. And yet another definition is that of a spectral radius of a matrix A, which is nothing but the maximum norm of all of its eigenvalues put together. That is, we take the norm of all of the eigenvalues, and the spectrum is nothing but the maximum norm. So, in other words, the spectrum is simply the radius of the smallest disk that can contain the entire spectrum of the matrix. For example, if we look at this matrix here, then we know that its spectrum is given by and a spectral radius which is equal to the maximum of norm of 1 and 3, which are the corresponding eigenvalues. Norm of 1 and 3 are simply the same, meaning it is equal to this. So, if one were to draw a circle of radius 3, then we know that all of the spectrum, which is, so 3 lies here, 1 will lie somewhere here, we know that all of its eigenvalues will be contained inside this disk. Okay. Now, we come back to the topic of calculating the structure of the Jordan matrix. In order to do that, we start with a special class of matrices A, where the eigenvalues are all distinct. Now, let us see what the theorem says. If the eigenvalues of a matrix A are all distinct, then the corresponding eigenvectors have to be linearly independent. So, let us see how that goes. So, these are the important properties associated with the eigenvalues of a matrix A, and these properties actually go on to decide the structure of the Jordan form, which we discussed before. So, in the next lecture, we will see how exactly the Jordan form is governed by the eigenvalues and hence the eigenvectors of a matrix A. Thank you.